everyone. Hello, everyone. Great to see you back for the HEAD seminar. Our first speaker today is Dominika Król, and she's working together with Pepe Fabiano and Martin Ellis here. Dominika did her PhD at Jagiellonian University in Krakow in Poland. She was here as a pre-doc in 2023 for half a year and then returned in November last year to the CfA as a postdoc. And today she's going to talk about ISO 137, a laboratory to diagnose AGN feedback. Take it away.
Thank you. Thank you, Ola. So I will be talking today about the project which I started.
I think it's on. I think it's on. You can direct it more upwards.
Okay, is it better?
I think it's okay.
Okay. I will be talking about the project which I started when I arrived here, working with Pepe Fabiano and Martin Elvis, and with collaboration with Anna Trindade and Ricardo Midei. And it will be about the ISO 137GO34, which, as I will try to convince you, is a great laboratory to study AGN feedback. But before I start talking about this particular source, let me tell you a few words. Why should we be interested in the feedback itself? And we know from multiple hints that the AGN feedback is a very important part of the galactic evolution. So here you can see the cartoon, which shows the theoretically predicted luminosity function of galaxies versus the observed one. And the departure, especially at the part of the plot corresponding to the most massive galaxies, requires some very energetic mechanism to be explained. And the AGN feedback is a great candidate for it. We also know from the very well-known M-sigma relation that there is a tight connection between the AGN, in this case, actually the mass of the supermassive black hole, and the velocity dispersion of the elliptical galaxies or the bulges which host these AGNs. So in general, we believe that the AGN feedback will have important role in galaxy evolution. So understanding it is very important in order to understand the evolution of our galaxies. We don't know how exactly feedback happens. However, we know few possible ways in which AGN can affect the interstellar medium in galaxies. And one of them will be radiation. So from the central part of the galaxy, from the nucleus, we have radiation, which will influence the ISM, photoionizing it, heating it, and also putting pressure. I will be focusing mostly on the photoionization. Also, there is a kinematic feedback, which probably the most spectacular one is the one which will be due to the jets. So ultrarelativistic outflows, when they propagate through patchy ESM, as you can see here from the snapshot of hydrodynamical simulations, this low density area here is jet. And you can see that when it propagates through this patchy ISM, it creates a lot of disturbances and influence the medium, interstellar medium. And the other phase of kinematic feedback will be winds and outflows, not necessarily relativistic. So I will be focusing in this talk mostly at X-ray data and what we can learn from X-ray data. And I'm doing it because X-rays in general are a very good energy band to study these processes and allow us to probe them more directly than other wavelengths. So when we think about AGN radiation field, we expect that the photoionized gas will emit in soft X-ray band. And also we can expect fluorescent signatures, and among them the famous neutral iron K alpha line. We measure the winds and outflows velocities in different wavelengths up to 1,000 kilometers per second. And if we think about shocks associated with this kind of outflows, they should hit the plasma to temperatures which will make them emit around kiloelectronvolts energy range. So again, X-rays are perfect wavelength to study. I will be focusing here on high resolution study of the single sources, and this way of studying the feedback gives us an opportunity to probe the feedback as it happens. So we can see basically how the AGN affects the host ISM while it happens. And here you can see an example of Markarian 573. You can see the Chandra image overlaid with all three contours. So oxygen-free line is a very good tracer of the photoionization. And in a lot of Seyfert-2 type galaxies, it creates this kind of biconical structures, which can be also very well traced, as you can see, by the X-ray emission. But on the top of that, in X-rays, we can also see the differences in the emission where we believe that jet interacts with ISM, seen here thanks to the contours at 6 centimeters. And much many examples of this kind of interaction can be found in the review of Fabiana and Elvis 2022. I will be focusing today at galaxy ESO 137G034, which is a Seyfert type 2 galaxy located not that far away from us. And at this redshift, the scale is that 1 arc second will correspond to 200 kiloparsecs. So we can resolve the impact of the AGN at this kind of scales. This is Compton-thick AGN. It is important for us because we're interested in diffuse medium emission. So we want to make sure that the nucleus is not, there's no pileup in Chandra data. So we need to make sure that the nucleus is not that bright. And in this case, it's basically observed. And I will be talking about the findings based on the 350 kiloseconds of Chandra data. And I will try to answer the question, what are the physical mechanisms behind this extended emission? And if we can disentangle the different feedback mechanisms at different parts of the source. So let me start with the azimuthal profile. So what you can see here is the extended emission azimuthal profile, so counts per pixel square as a function of the angle. And we measure the angles from the western part of the sky to the north. And what you can see here is this beforehand mentioned biconical structure of the X-ray extended emission. And based on this, we divided our source into the 4 regions: 2 cones, southeastern and northwestern, and 2 cross cones areas. The question, though, also is how much of this extended emission at what energies is actually coming from the diffuse gas, and how much of it is basically the point spread function of the nucleus. So in order to answer this question, we checked the excess of data over the point spread function at different energies. And here you can see the most broad range between 0.5 to 7 kiloelectronvolts. And you can see the comparison, and in all of those plots I will show in a second, you will see the comparison between the point spread function profiles and the extent of the data at cones and at cross cones. And you can see that if we take into account this whole energy range, this source is really extended. We can see extents up to 10 arc seconds, which would correspond to around 2 kiloparsecs. And also the cross cone emission is extended. Now let's dive into it and see at what energies the source is extended. So in the softest part below 1.5 kiloelectronvolts, both cross cone and cone emission is extended. But when we start to increase the energy, the extension decreases, with still up to 3 kiloelectronvolts, both cones and cross cone having extension. But below 4 kiloelectronvolts, only cone region has extensions. And this region is not that extent in the high energy range, which some of the other Compton-thick AGNs actually show the pretty significant extension. So in this talk, I will be focusing on soft energy bands. When it comes to cross-cone emission, I showed you before the biconical structure, and basically it arises from the fact that we have this radiation field from the center part of the source, and then we don't expect that much of the radiation, photoionized radiation, in the cross-cone regions, because we expect that torus will block most of this emission. However, we can think of 2 possible mechanisms behind this cross-cone direction extension. One of them would be the leakage of the nucleus emission, And the other would be interactions and lateral outflows, which arise due to the jet interactions with patchy dense ISM in the galaxy. In this case, though, since cross-cone emission is very soft, we believe that we can conclude that, unfortunately, I think it cut part of the slide, but we can conclude that the soft nature of the emission points out towards the second solution. So we believe that this is basically an interaction between the jet and patchy ISM, which creates these outflows in the lateral directions. The situation is slightly more complicated when it comes to ionization cones. We extracted spectra from the cones, and we found out that the best fit model requires two components: thermal plasma and photoionized gas emission. And what will be important later, we found that thermal plasma emission dominates at energies below 1.5 kiloelectronvolts. So in order to understand from which part of the sources these two emission components arise, so in which part of the sources the kinematic versus radiative avenue feedback dominates, we leverage the Chandra's spatial resolution in order to try to understand what mechanisms are dominant in what source regions. And when it comes to those two different mechanisms, photoionized gas emission is expected to be, sorry, it's not my laptop, so it's always a bit tricky.
Yes, this.
I think it also, yeah, I pushed
Yeah.
something.
It's the button below that. This arrow button is the one that is causing that.
I guess I can just start to use touchpads to point
Now it
instead
should
of
be.
Thank you very much.
Sorry.
Sorry. So this different emission mechanism, we can expect that photoionized gas emission will be associated with O3, as I mentioned, tracer of the photoionization, of ionization. And so we can use the fact that we also have observations in O3 emission line from Hubble Space Telescope and check how these two profiles behave when we compare them with each other. So here you can see the northern cone structure. You can see the northern core region. You can see the contours of the O3 emission overplot on the Chandra image between 0.5 and 4 kiloelectronvolts. And what we done is we checked the ratio between O3 emission and the X-ray emission in the softer band. And we found that starting from around 2 arc seconds, so around 400 parsecs, the ratio is relatively flat, which can be related to, which is consistent with the photoionized gas emission. And in the case of the gas, with the density profile changing as distance to the power of -2. When it comes to thermal emission of shock-heated gas, of shock-heated plasma, we expect that it will be associated with radiolobes, since in general we expect a lot of shocks there. There is in literature the paper which details that we expect also neon emission lines excess at that part, and based on the spectral results which I showed you before, we expect that the thermal emission will dominate below 1.5 kiloelectronvolts. So we plotted in this time, we compared our X-ray data with the jet image seen at 3 centimeters. And we found out that if we zoom into this part of the plot and we plot the O3 versus X-rays ratio, tax ratios, we see the dip in this ratio at the parts which are coinciding with the radial lobe. So basically, we have excess of X-ray emission, which we would expect from the presence of shocks. Also, we can see the excess, not very significant, at around 2.5 sigma level of neon emission over different emission lines at this region of the galaxy. And also we see higher values of the soft emission, so below 1.5 kiloelectronvolts over the harder. So all in all, this is consistent with emission of shock-heated thermal plasma dominating this part of the source. So we have the ionized emission in general in the cones. We have on the top of that, in the inner parts of the sources, we have significant portion of emission caused by shocks and heating of the gas. But in the last part of the data analysis, which result I want to bring your attention to, is certain energy dependence, which we can see in southern east cone region. So in the azimuthal profile, which I showed you at the beginning, so in counts versus pixel squares, as a function of the angle, you can see this kind of double peak structure in the southern eastern cone. And it can be better understood if we divide our data if we divide our profile to profile between 0.3 and 1.5 kiloelectronvolts, in which then the maximum is corresponding to one of these peaks. And you can see here the position of the maximum overlaid on the image in this energy range. And also the other peak can be, the other peak erases from the emission on higher energy, so from 1.5 to 4 kiloelectronvolts. And here you can see the map at that energy range, and you can see where this emission has a maximum. So when we take a closer look to this ionization cone, we created the regions which would be around this maxima, and we started to examine the ratio of the O3 to X-ray emission. And as you can see, one of them follows pretty well the general trend. However, overplotting the ratio for the direction corresponding to maximum on the higher energy ranges shows completely different behavior of the flux ratios below 3 arc minutes, which would correspond in that redshift to around 600 parsecs. So something interesting and something different happens at these regions, and we can see different properties of the emission. It can be also seen in the hardness ratio map. So here you can see only this part of the profile and the hardness ratio, so divided counts between 0.3 and 1.5 kiloelectronvolts and 1.5 to 4 kiloelectronvolts at different sub-regions of cones in that directions. So you can see completely different behavior of the profiles. And this one probably is caused by the different properties of ISM and is to be explored in multi-wavelength data. But already the literature result from the literature from JWST observations sees that they see that the kinematic major axis of the rotating gas actually comes from one of these regions. So this difference in the emission seen also in X-rays is probably due to very different properties of ISM at that part of the source. So the summary is that we were able to deduce using the Chandra spatial combination of spatial and spectral resolution, we're able to deduce which avenues of feedback are dominant at which part of the galaxy. We found that the thermal emission, which is dominant below 1.5 kiloelectronvolts, is dominant at the inner part of the cone. And on the top of that, we also see the emission of photoionized gas, X-ray gas. We also found that there is a cross-cone extended emission, which seems to arise due to interactions of jet and patchy ISM due to its very soft nature. And we also found hints, we found out different features of X-ray emission depending on local ISM conditions, which can be explored more in multi-wavelength data. So in general, based on this X-ray analysis, we can see that we can in the source see multiple different avenues of feedback, and we can connect them to specific sources of origin. Thank you very much.
very much. Do we have any questions in the room? Yeah, you, I think was first.
Thank you, very nice work and beautiful thoughts. Do you have any plan to look at these galaxies by using some optical image over the eye view to get the high spectral resolution of some emission lines to get the kinematics of?
Yes, so this is actually work in progress, which is happening right now. So first of all, we have Hubble data based on which we will be able to build spatial resolvability diagram. So this will be the one diagnostic which will be added here. And also our collaborators shared data with us from the VLA, in which you can see the kinematics of the gas. So that is work which will to come.
Maybe I missed it. What's the black hole mass? And if you have it, how was it determined?
To be honest, I don't remember on the top of my head in this source. I will check and get back to you later, sorry.
Very nice results. It's exciting. So I have a question about the energetics. So how much energy is deposited with this shock into the eye?
So when we look at the spectra and we compare the energy fluxes contained in the thermal plasma emission and photoionized emission, they are comparable with each other. So that would be basically comparable to each other parts. It'll be.
Yes, please.
I'm curious, you were looking in the southeast cone at the ratio of O3 to the X-ray brightness, and you noted that at the more southern angle that there's this deficit at like 1 to 1.5 arc seconds. I'm curious about in the more northern segment, the deficit at like 2.5 arc seconds, if that's something you've looked at?
You mean this part here?
Yeah, in the blue region at 170 to 215.
170 to 215. Yes, so this is coinciding with the kinematic measure axis, which is measured by JWST. So whereas the deep in general would suggest that we have the excess of X-ray data, and this is of X-rays, and this is more or less where we see the radio jets. So those deeps here would be probably due to the shock emission adding on to top of the photoionization. But when it comes to this southern part, this red part, it's probably is connected to the basically ISM densities and maybe some enhancement of either O3 emission or. Yeah.
Anything? Oh yeah.
I think can you show the accidentally the map which showed a similar symmetry toward that direction right there?
Yes,
Yeah.
you
So
can.
go, yeah. That's part of the excess in your ratio.
Yes, that's part of the excess, and also you can see in different wavelengths, which we plan to compare further. You can also see the ALMA excess there, so we can also see molecular clouds, basically emission there, CO.
Great. I don't see any further questions, and I think there's also nothing on Zoom, right? Okay. Let's thank Dominika again.
Thank you.
So it's
Hide video panel.
where's that?
This.
No. So, oh, there it goes. Yes. Don't know why it was.
If you go to more, then height floating meeting controls.
Oh, thank you.
Okay, so let's start with our second speaker. It is my pleasure to introduce Jack Sayers, who's a research professor of physics at Caltech. And Jack ran the marathon this Monday, so thank you, extra thank you for being with us today. Yeah, so Jack completed his PhD in physics and he got it from Caltech back in 2007. And then he had a series of junior and more senior postdoctoral roles in Caltech and JPL up until year 2016, where he was a research assistant professor of physics at Caltech. And then he became a research professor of physics at Caltech in 2019. So this is the position that he's currently holding. And today he'll be talking about clusters of galaxies and how to probe them using different probes, I would say. So thank you, Jack, and take it away.
Okay, great, thanks. And the mic is working okay?
Yes.
Okay. Yeah, so basically I'll be talking about utilizing multiple observational probes and to study the geometry of clusters in two separate ways. One is the geometry of major mergers between similar mass objects, and the other is studying the overall triaxial geometry, triaxial elliptical geometry that we expect for the more quiescent relaxed objects.
Oh, for the first one, you have to wait and then.
Yes, thank you. Okay, so to first put this in context, so here's a movie showing the formation of galaxy clusters over cosmic time to just illustrate these two different geometrical quantities. And so if you pay attention in the middle, around z of 1.2, you're going to see a fairly major triple merger. And then later on at z of 0.7, you'll see a binary merger occur. And so these are the merger events that I'll be talking about in the first half of the talk, just a visual illustration of what's going on. And then if you trace this towards the end of this simulation, as the cluster is starting to relax and become more quiescent, you'll see that it has this elliptical geometry. And so this is, on average, these objects, as you all know, collapse to be much more elliptical than round. And so that'll be the topic of the second half of my talk. Okay, and so John gave me some instructions of the audience here, and he said it might be worthwhile to just have a quick intro to what galaxy clusters are. So I'll go through this. I know it's review for a lot of you, but these are objects, they're the largest and most recent objects to form in our universe. They sample a large enough volume that their overall composition matches that of the universe as a whole. So they're mostly dark matter with about 15% baryons. And most of those baryons are in a diffuse 10 to the 8 Kelvin ionized gas. And so just visually from a simulation, what they look like, here's the dark matter distribution, very clumpy. The gas is much smoother and more diffuse, and this is what the stellar component looks like. So why should we study cluster mergers? To start off, they're interesting. I mean, they're the most energetic events since the Big Bang, so I think they're intrinsically interesting for that reason. It also allows us to probe physics in a fairly unique environment. It's a very low density and very high temperature plasma. And within this environment, for example, during a merger, there's shocks induced in the ICM, and the properties of these shocks are sensitive to a wide range of plasma physics. For example, the electron-ion equilibration timescale, diffusion, and so on and so forth. Mergers are also, beyond studying the ICM plasma, they're a useful probe of the properties of dark matter. And for example, I'm sure all of you are familiar with this famous picture of the bullet cluster with the gas in pink and the total mass distribution in blue, just showing that the gas has decoupled from the dark matter as a result of this collision. And this decoupling has provided some of the strongest constraints on the self-interaction cross-section of dark matter. So historically, the way that we've studied these mergers primarily is Chandra is a great probe with its high angular resolution. It can measure these sharp edges from the shocks. And so you get a really good handle of what the plane of sky distribution of the gas is from Chandra. You can then combine that with lensing information, for example, from HST, to give you the plane of sky distribution of the dark matter. And for clusters like the bullet, where the merger itself, the initial velocities are primarily in the plane of the sky, these features stand out nicely in these plane of sky images. So you can see, you know, for example, these sharp features in the gas here, this bow shock there. You can also see nicely the separation between the gas and the dark matter. And so you can really learn a lot from studying these mergers. But the issue is, you know, if we're looking at the whole sky, very few of these mergers are actually oriented with this favorable orientation that we can study them. And so can we move beyond this to study clusters of any arbitrary orientation? And so this, we created ICM shocks to do just that. And this is a project being led by Emily Silich, who's a PhD student at Caltech in our group. And she was actually here last year visiting as a pre-doc at SAO. So many of you probably know her from her time here. And so the idea is that by combining additional probes, we can study cluster mergers with any orientation. And so the main idea is we have all these observational probes, which I'll show you in just a moment, and we then compare them to forward modeled simulations that have primarily been generated from Elena and John here at SAO, and Paola's now working in the group as well on this project. So far, we've published 2 papers. One that I'll talk about in some detail is our study of this first cluster, MaxJ0018, that we've learned a lot of interesting things from that study. The other is a paper just describing our full sample. So we actually have data for a set of 8 clusters in total. And I'll say a little bit about where we are on this full sample analysis. So to start off, here's the observational probes that we're using. So from the upper left, again, we're using X-rays for the gas distribution in the plane of the sky. This is a surface brightness image that just shows you the overall distribution, and then a temperature image, which gives you a handle on both the spatial distribution and the thermodynamics of that gas. In the upper right is a projected mass map that we've reconstructed from HST lensing data, primarily strong lensing constraints. The new things that we're adding for our study is we now have a map of the gas velocity. This is the line of sight velocity of the gas. And we're getting this from the Caltech submillimeter observatory using the kinematic SZ effect. And this is just a Doppler shift of the CMB that gives us a handle on this line of sight velocity of the gas. And then for the dark matter velocity, we're assuming, you know, in the pure cold dark matter paradigm, the galaxies themselves are a good tracer of what the dark matter is doing. And so we have spectra of hundreds of individual member galaxies that we've collected with Keck. And in particular, for each cluster, we tend to have between 200 to 300 individual member galaxies. And we can average and aggregate those together to get a handle on what the dark matter velocity is in the line of sight. So by putting all these different probes together, we get a pretty good handle on what's going on spatially between both the gas and the dark matter in the plane of the sky, along with what's going on in terms of the velocity component along the line of sight. And so, as I mentioned, in total, we have data to study 8 mergers. And as far as we're aware, this is the first time the gas velocity has been used in these sorts of studies. And so if I start again with MaxJ0018.5, which is the first cluster in our study, an interesting discovery that we came up with is that the dark matter and the gas appear to be moving with much different velocities. So in the upper right, this is the dark matter traced again by the galaxies. In the northwest region, you can see it's a strong negative velocity. And in the southwest, or the southeast, excuse me, it's a strong positive velocity. And if you then look at the gas velocity, it's almost 180 degrees out of phase. And then we have this strong positive velocity to the west and a strong negative velocity to the east. And this is actually analogous to the positional decoupling that we saw earlier in the bullet cluster and that you can see here in the baby bullet cluster. And to better visualize what's going on here, of course, the whole reason that there's this spatial decoupling that we saw in the bullet cluster is because the ICM is collisional, and at least in standard cold dark matter, the dark matter is not. And so as the merger progresses, the gas slows down, whereas the dark matter doesn't, at least not as quickly. Okay. Sorry about that.
I think slides.
Yes. I'm not sure what was pressed there. Oh boy. Okay, so, the way to visualize this is that during the merger, the ICM is slowing down, whereas the dark matter is not. And so you can imagine your telescope here, and you have cluster 1 coming in from the left and cluster 2 coming in from the right. The ICM is lagging the dark matter. And so if you position your telescope here, the left-hand side of your field of view, you're primarily seeing the dark matter from cluster 2 and the gas from cluster 1. And then vice versa on the right-hand side of your field of view. And so from this, you then end up with, in this spatial image, it looks as though the two components are moving in opposite directions in the two sides of your image. It actually takes a fairly specific geometry to cause this, in that you need the velocity aligned close to the line of sight, but not perfectly aligned. And you also need the epoch to be very close to pericenter passage. And so from the simulations, this appears to be fairly rare. It's a fairly short-lived phenomena that requires this very specific geometry. And at least anecdotally, we only see it in one of the 8 systems that we've looked at. So it appears to be rare in what we've actually observed. And for some reason, it saved all of these extra pages. So let me.
It's only 300.
Was it 300?
Yes, 290.
Oh gosh. Okay, let's do this. Oh, and
You missed it. It was somewhere.
it was in the middle here.
Yes.
Yes, there we go. Okay, and then let's start from here.
No. In the bottom right.
Yes, thank you.
Yes.
Yes. Okay, thank you. And again, sorry for the technical challenge. So if we then return to what we've learned of this particular system from these multi-probes, again, we've actually constrained the geometry quite well. So we know that this system is within a few tens of years post-pericenter passage. The inclination of the initial velocities relative to the line of sight, again, they're not perfectly aligned, but it's a relatively small inclination of between 27 and 40 degrees. The impact parameter is fairly small. It's less than about 250 kiloparsecs. It's a major merger, so the mass ratio is somewhere between 1.5 and 3. And the initial velocities are quite high, somewhere in the range of 1,700 to 3,000 kilometers per second. And this is reference to the initialization of the simulations we're comparing to. So this is at a separation of something like 2 to 3 megaparsecs. So despite what we've learned, there still are some mysteries in this system. And in particular, you can see this Chandra image in the upper right, and there's an annular region that we've identified. And if you extract a profile across that annular region, you can see there's what appears to be a surface brightness discontinuity. And in the existing Chandra data, depending exactly how what model you assume, it's somewhere between about 2.5 and 3 sigma that we measure this discontinuity. And so fortunately, we have some new observations with Chandra coming up. The first one is scheduled for September. And so we should have much deeper data within the next few months to really firmly establish whether this is a discontinuity there. We also have new data as Z observations coming from the Toltec instrument on the LMT in Mexico, and these are very high angular resolution as Z data. And so I should say, even with the deeper Chandra data, we have no realistic expectation that we could measure a temperature discontinuity or lack thereof on the two sides of this edge. And so we still wouldn't be able to firmly establish whether this is a shock or some other feature like a cold front from the Chandra data alone, even with the deeper data. But in combination with the SZ data, where we would be able to see a pressure discontinuity if it is a shock, this would allow us to firmly establish what the nature of this discontinuity is. And I should say what's particularly interesting is because we know the geometry of this merger so well, if we can establish this as a shock, it's actually an equatorial shock, which are very rarely seen. Most of the shocks that have been studied in the past are axial shocks along the axis of the merger, whereas this one is actually orthogonal to that axis. It would, as you can see here too, also require a significantly different inclination to the line of sight than what we've inferred so far. It's not excluded by the analysis we've done so far, but it would have to be much closer to the line of sight. Okay, so going forward from there, we are working on the full sample now. I should say our initial analysis, we use by-eye comparisons between the observables and the forward modeled simulations. And this was fine, but it's a very binary criteria. We said if the simulation snapshot is between value X and value Y, then we say it's good, and if it's outside that region, we say it's bad. And so what we're now doing is we've established a set of chi-squared like comparison statistics so that we can actually quantify the goodness of fit between the snapshots and the observed data that gives us a much more continuous view of what's a good fit or what's not a good fit. And in addition to allowing us to better establish, more statistically rigorous, boundaries of which geometries are allowed or not, we're hoping that this will hopefully alleviate a lot of potential biases in the initial analysis. And for example, you can imagine if there's low signal to noise features, they're easily visually identifiable. And so we're worried, for example, maybe we've put too much weight in matching those features. On the flip side, if you have, very small angular extent features that are very high signal to noise, it's easy to kind of gloss over those and not include them appropriately in your comparison criteria. So this is ongoing now. Emily's working on this, and we hope to have this new pipeline set up in the very near future. And we have a few clusters that we're studying as part of this pipeline. We've also updated our processing of the observed data, as you can see. This is the same kind of panel of figures that I showed earlier. And so this is our old friend Max 0018.5. We do have more spectra from Keck now that are included in the galaxy velocity map, but I won't say too much other than that about this system. I will note in all of these, the X marks the peak of the mass distribution from Hubble, and the circle marks a 500 kiloparsec radius region. So then another system we're looking at is Max J2129. And so you'll see here, as I noted, if you look at the galaxy and the gas velocities, they're very well aligned in this system. Both have a strong positive velocity to the west, a strong negative velocity to the east. What's interesting here, the gas, so this system is clearly elongated east-west. And for an X-ray surface brightness in the top middle, you can see there's a bit of an offset in the X-ray emission towards the east of where the mass peak is. And this seems even more prominent in the bottom right, where we've reconstructed the gas density from the SZ emission. And so that's interesting. Again, this system is very elongated east-west, has this positional offset, but the velocities are also quite high. And so the plane of sky features are more indicative of a merger occurring in that orientation, whereas the large velocities tend to indicate something along the line of sight. And so we're interested in modeling this in more detail to disentangle these features. Another system is Max J0454. In this case, the magnitude of the velocities is much lower than the other two systems. So we went into this assuming that this is a plane of sky merger. You can see again, it's elongated quite a bit east-west. What's interesting here is in the bottom panel, the temperature map. So you can see to the north and to the south, there's some very hot regions of gas. And interior to these, there's much colder regions. And so that's a little bit mysterious. Again, given that the merger itself seems to be progressing in the east-west direction, why there's these features north-south, and again, why the hotter gas is outside of the cooler gas. And so this is another interesting system that we're working on studying right now. Okay, so I'll move on now to the other set of geometric tests of clusters that we're working on. And so this is the project itself is called Clump 3D. And the idea here is that we're fitting triaxial models to the clusters themselves. And the way we're doing this is if you have both SZ and X-ray data, they depend on the gas in different ways when integrated along the line of sight. And so if you combine them together and assume that they're both probing the same gas distribution, you actually get a handle on the line of sight extent of the cluster. And so then from the imaging in the plane of the sky, you get a full three-dimensional picture of what the geometry is. So we can then further, if we include weak lensing data, we make the assumption that the ICM and the mass are co-aligned with each other so that the major and minor and intermediate axis are all in the same direction. We make no assumption that they have the same axial ratios, but just that this is the alignment of the total mass distribution. And from there, you can then use the lensing data to constrain a 3D distribution of the total mass. And this is a nice way for testing gravity and cosmology, and it is one example that I'll quantify a little bit later within the talk. For example, if you turn up the self-interaction cross-section of dark matter, you get rounder halos on average. Another scientific topic that we're exploring here is, of course, because of triaxiality and projection and orientation, the per cluster uncertainty on weak lensing mass estimates is quite large. It's of order of 30%. And so it really prevents you from making detailed per cluster studies from those spherically estimated masses from weak lensing. But now that we have a handle on what the 3D geometry is, we can get a much more accurate per cluster measurement of the total mass. And for example, you can compare the pressure required to offset gravitational collapse with the total thermal pressure measured from the gas probes in the SD and the X-ray. And the difference between these then gives you a handle on the amount of support from non-thermal motions. And for example, these non-thermal motions, at least on large scales within the cluster, are expected to be due to incomplete thermalization of accreted material. And so it gives you a handle on the physics of what's going on for thermalizing the accreted material onto the cluster. So we did this for 16 clusters in the HST clash sample. Here's the two main papers that resulted. I'll just quickly mention the results from that. One is that for the geometry, we found slightly more extreme minor to major axial ratios. So we actually found more elliptical clusters in the dark matter than what would be expected from standard CDM. It's only at about 2 sigma, so nothing conclusive there. The other thing that we found is this non-thermal pressure fraction. We probed it in the center of the cluster, and on the bottom right in blue, you can see our 95% confidence region from this study. We basically found that there's very little non-thermal pressure in the cluster cores, less than 10%. And at the time, the only direct measurement was from Hitomi in the Perseus cluster, which is shown in purple, which is consistent with what we found. And of course, as we all know now, GRISM has more updated results, also finding very low values of non-thermal pressure in the centers of clusters. So with CLASH, we were limited both in terms of sample size and also in terms of the quality of the X-ray data that were fairly shallow Chandra observations. And so we're now working on applying this to the XMM Newton Heritage Program Checkmate, which is about 120 clusters. There's 2 separate samples. One is a volume limited sample in the local universe. The other is a mass limited sample extending to higher redshift. All of these, by definition, they have extremely deep XMM data, since that's how the program was defined. They also all have good SZ data, and at the moment we have weak lensing coverage for most of the sample of order about 100, and we're quickly working to fill in the full 120 or so. So this is perfect for applying our clump 3D formalism. And so Junhan Kim, who is a postdoc working in our group at Caltech and is now faculty at KAIST, he basically transitioned the pipeline we had built for CLASH and reconfigured it for the checkmate data. He did this just for the gas observables, the SD and the X-ray, and applied this to one cluster as a test sample. You can see he found extremely precise constraints on the axial ratios for this system, which is demonstrated on the right. Adriana Gavidia, who's a PhD student in our group, has now taken this over, and she's extended the pipeline to include weak lensing data. And so on the bottom left is the profile of non-thermal pressure that she extracted for one single test case. And you can see the precision she's getting for one cluster with the checkmate data is close to what we got for the ensemble of 16 CLASH clusters. So this is just a visual demonstration of how much better the data are that we're working with right now. Another topic that I mentioned was the weak lensing mass estimates, both in the spherical and triaxial basis. And you can see in the upper right here, purple is what you get with the standard spherical modeling, and green is what we then get in the triaxial basis. And so you can see for this particular cluster, they differ by a fair amount. And this is again the advantage of having this triaxial modeling, of we can eliminate this bias that you get from orientation and projection. So looking forward to the full sample analysis of all 120 objects, for example, we expect to obtain percent level constraints on the non-thermal pressure fraction out to about the virial radius, which is roughly R200. And so for some context here, simulations differ by the order of 10% in the predictions of the non-thermal pressure fraction at that radius. And so we should be able to easily distinguish those. As another example of some of the science we can do from the simulations in the upper right here, if you scale to the critical overdensity as a scale radius rather than the matter overdensity, the prediction is that you will see an apparent evolution in the non-thermal pressure as a function of redshift. And if this does exist, we should expect to detect that at something like 3 to 4 sigma. Another probe of the thermalization history, you can think of, instead of this profile of non-thermal pressure, you can think of just the total integrated temperature as a proxy of how well thermalized the gas is. And so, for example, if clusters that formed more recently, you would expect them to be less well thermalized, and so the temperature would be suppressed. And similarly, clusters that had formed further back would be more thermalized and have a higher temperature. And so on the bottom here is just a scaling relation between temperature and total mass, and it's color coded as a function of axial ratio. And so the axial ratio is a good proxy of formation time. Of the rounder the cluster is, the longer ago it formed, the more triaxial it is, the more recently it's formed. And so you can see in this simulation, they find that the more extreme the triaxial ratio, so the lower the value of this axial ratio, the lower the temperature is relative to the average relation. And so this is something else we can probe, and based on the prediction from the simulation, if it is at that level, we should detect that at something like 7 sigma from the full sample. Getting back to using these axial ratios as a probe of self-interacting dark matter. So the plot in the middle here is just showing what the distribution of major axial ratios should be for universes either with the standard cold dark matter paradigm or for different values of self-interaction cross-section. And you can see as you turn up the value of the self-interaction cross-section, the distribution shifts to the right, so shifts towards rounder halos. And our expectation based on the constraints we can obtain for the axial ratios is that for the full sample of checkmate clusters, we could constrain the cross-section to about plus or minus 0.15 centimeters squared per gram. And for context, this is similar to the best constraints at cluster scales that people are obtaining from inner mass profiles. But now instead of probing, this very high density region at the center of clusters, where you're very prone to systematics from the baryons in the center of the cluster, we're now probing at large megaparsec scales where some of the intrinsic biases should be mitigated. The other thing that we can do is weak lensing has become effectively the gold standard for cosmology with halo abundance measurements. And so, for example, surveys like Euclid are trying to constrain the average level of scatter and bias at the percent level in order to really realize the full cosmological potential of those surveys. And so if you want this percent level verification, to date, it's all been done in simulations. Of people take distributions, clusters of varying geometries from simulations, fit spherical weak lensing models to those, and then use that to debias the lensing masses that they get from the survey. And so with checkmate, because we can measure both the spherical and the triaxial masses, it'll be the first real verification of this. And we think for the full sample, we can actually get down to a percent level observational verification of this bias. So the last thing I'll mention is that, we're talking about percent level constraints on a lot of quantities from checkmate. And if we do that, you actually start to run into things of, we have this SZ selected sample. And if you were to, for example, assume that the SZ selected sample is a good representation of the universe in terms of geometry and orientation, you'd actually end up with some biases that are larger than this percent level goal that we're going to. And so Harshita Saxena, who's a second-year PhD student with us at Caltech, has been working on this problem. And so what she did is she implemented the MMF3 detection algorithm that was used in the SZ survey that originally was used as the basis for forming the checkmate sample. She generated 1,000 mock universes with clusters with triaxial shapes and random orientations, ran this detection algorithm on those 1,000 mock universes, and formed mock checkmate-like samples. And so what she found is, as you might expect, that there is a preference for line of sight elongation, that the SZ signal is boosted preferentially when the cluster is elongated along the line of sight. And so you're more likely to detect those objects. And so you can see this on the bottom left of the orange and red lines are just for random selections of clusters from the universe to give you an idea of the stochastic Poisson noise from the fact that for computational reasons, we could only do this on 1,000 mock universes. And so you can see they vary at, kind of the percent level, but the actual selections of both the tier 1 and the tier 2 checkmate samples are skewed very far towards larger values of cosine theta. And theta is just the inclination relative to the line of sight. So cosine theta of 1 is that the major axis is perfectly aligned with the line of sight. So because of this preferential selection of line of sight elongated clusters, you actually get a bias in the weak lensing mass that you determine. And so this is shown on the two plots on the right for tier 1 and tier 2. So blue is what we get for these checkmate-like selected samples of the ratio of weak lensing to true mass on the y-axis versus true mass on the x-axis. And so you can see, as expected, as you shift to lower mass, which is closer to the survey detection limit, the bias becomes more pronounced, and it's at the kind of 3 to 5% level. At the high mass end, where effectively the survey detects everything regardless of orientation, the bias goes away. Okay, so I think I've utilized all my time, so I'll end there and just kind of leave with some of the take-home messages of some of these geometrical tests that we're doing and the science that you can achieve from that. And thank you, everyone.
Questions for Jack?
Thank you. Maybe I missed something. So for this kind of gas and dark matter decoupled atoms, can you find any residue from the secondary cluster, which, you know, from the stellar velocity, from the galaxy velocity dispersion things, or from something similar to see the residue from the secondary cluster?
You're talking like a bimodal distribution in the galaxy velocities, for instance?
Something like that, yes. Because now you can see that the galaxy have different kinematics from the gas, but you have a very long radius. So for some members, is there any of them from the secondary cluster region?
Yeah, in practice, so for the systems we're looking at, they're pretty large mass ratios, and so and they are overlapping to a large degree. Where most of them we think we're viewing pretty close to pericenter passage. So there's a lot of spatial overlap between the galaxies, and so we haven't looked at this in detail, but for example, you know, a lot of the distributions, you know, they're kind of broadened out and non-Gaussian, but they're not kind of distinctly bimodal. If that makes sense.
One more question.
I have a question about the second half of the talk. So we know that many CD galaxies are elongated. Do they actually trace the global cluster geometry, or is it completely independent? Because we can get their shapes from optical images.
Yeah, and we actually looked at this a bit in Clash, just in 2 dimensions in the plane of the sky, and there is a reasonable amount of co-alignment there. I'm off the top of my head, I know there's been a lot of other studies looking at this, and I in a quantitative, you know, quantitatively in detail, I don't know the answer, but I think in general there is a fair amount of co-alignment there.
Any more questions for Jack from upstairs or Zoom or? So I mean, I understand that what you mentioned, some of the checkmate clusters, at least their thermal properties have been mapped to the innermost region so as to probe dark matter, like the particle nature of dark matter, including self-interacting dark matter. So I was wondering how the constraints on self-interacting dark matter coming from mapping the cluster down to the innermost regions compared to what you were mentioning in the second part of the talk.
Yeah, so the most recent constraints I've seen for, you know, mapping the inner density profiles are in this ballpark. I think that it's maybe a little better than plus or minus 0.1 from the most recent results I've seen, but it's the precision is pretty comparable to this. Is that what you're asking?
Yeah, so essentially how they differ basically, so whether you're able to like place more stringent limits, because even strong lensing of other clusters, some of the Hubble frontal field clusters, they give sort of these upper bounds.
Yeah. So as far as raw precision, we're in the ballpark again. I think some of these other probes, including, you know, the inner density profiles of clusters, there may be, you know, kind of a factor of 2-ish more precise. But I think the hope here is that, you know, this would be totally different systematics, and it's also probing, you know, kind of a lower density regime at much larger scales. So it's still complementary to those other techniques.
Great, thank you. Any other questions for Jack? Okay, so if not, let's thank our speakers.